We're going to be doing heat treatment, and the reason why we're doing this experiment is to determine these unknown samples. We have 4 of them, and to become familiar with heat treatment of steels. So you're going to take a sample 1 through 4. On your sign-in sheet, it will give you a heat treatment sample number, and you're going to take one of those today. We're also going to drill a hole in the edge of it, because when you put it in the furnace, in order to get it out of the furnace quickly, you need to have a little wire or something that you can hook with a rod to quickly get it out of the furnace. There'll be 6 or 7 of them in the furnace at the same time. At the end of the semester, right now you're kind of doing this lab, not exactly knowing why or what you're going to do with it later on, and we'll talk about that in class pretty soon. You're going to write a report, basically an experimental procedure, how you do it. You're going to write, you're going to take the data, you're going to look at the data different ways with Excel, and try to determine, how hard did it get at different cooling rates, and eventually from that information you should be able to make a good assumption as to what type of steel it is, at least the carbon content of the steel. So that's the goal. By doing these heat treatments, you're going to determine what the carbon content of these unknown samples are. So don't lose your sample, and don't get it mixed up with someone else's sample. Okay? How would you do that? These samples are all in a condition in which they can be machined or drilled. Okay? So we're going to drill a hole in it. We're also, at this point, it'd be a good time to make some marks in it that sets your sample apart from everyone else's, so no one else mistakes your part for their part. Okay? You could take a file and put some grooves in the edge of it. You could take a hacksaw and cut into it a little bit. And so you want to mark this in a way. You could even take the drill and maybe put a couple little dots on it, with the tip of the drill in different locations, so you know that it's yours, and then other people know that it's not theirs. That's really the more important part, because it's great to be able to identify yours, but if someone else mistakes yours as theirs, then you can't find it. Someone else has it. Okay, and then that screws up all the data. Once we get, you're going to go through 4 different heat treatments. Okay, you're going to do an air cooling. You're going to put it in the furnace, let it air cool. You're going to do a oil cooling, a water cooling, and then at the end we're going to put all of them in the furnace together, heat it up, and let it slowly cool in the furnace. And that's an annealing. So that would actually be the slowest cooling rate. We do that at the end though. Okay. The reason is because you get a lot of scale on the surface from the iron. You get a lot of iron oxide because it's cooled for such a long period of time. And if we would do that first, then you'd have to really spend a lot of time sanding it off to get down to some good steel. You lose some carbon on the surface as well too when you put it in the furnace for a long period of time like that. So so that's essentially the experiment. And you're going to take hardness readings after each one of those cooling rates, and initially when you first start, before you start out. And then all that data is going to be placed on the one of these computers over here, and on a spreadsheet. Okay. Then the data will be put on D2L, and you will use everyone's data for doing your report. The idea is that anytime you get data, sometimes the data is incorrect, and you got to kind of be a detective to figure out. Well, everyone else had 56 hardness for this particular sample, and this person had 23. Okay, probably something went wrong with that particular experiment, and try to determine what data to use and what not to use. Okay, so what I'd like you to do is grab one of these samples, and then we're going to drill a hole in it. We're all going to drill a hole in it, and then we'll come over here and we'll use the hardness testers. They're Rockwell hardness testers, and one thing we got to be careful though is that these were cut on a metallurgical abrasive saw, which has water cooling on it. And the idea was to not heat treat them while you were, just cutting them off. Okay, and they're in a condition that can be machined. If I were to, let's say, heat this up to 1300 degrees, and you could do that with an abrasive saw. Ever see them? They get red hot when you're cutting them. Cutting a piece of steel or something like that, you use a normal abrasive saw. You might heat treat these to a point whereby you couldn't file them, you couldn't drill them, and that's going to throw off your initial hardness of what this material is, how it came to you. Okay. Unfortunately, as it cuts through the bottom side of the part, it gets really thin there, and it's hard for the coolant to get down there. So this little burr that's left on the edge, that'll probably actually be fairly hard, and possibly some of the steel right around it. So you don't want to drill your hole there, and you don't want to take a hardness there, because that might be, give you a wrong reading. The other thing is where it got stamped. You see it's got a number 1 on this one. Where it got stamped, you probably work hardened it a little bit in that area, so you probably won't want to do a hardness there. You never do a hardness closer than a couple diameters of the indentation away, okay? Because when you take a hardness, you're actually plastically deforming the material, and in the area around that, theoretically it's going to get a little bit harder because of the work hardening of the metal, okay? Okay, so everyone grab one of these. Okay, at this point with your heat treatment sample, what you're going to do is you're going to drill a hole in it so that we can put a little wire through it. You're going to be using like the 035 wire that we use for welding. You're going to put it through the hole, and you're going to twist it so that it kind of sits up. When you put your sample in the furnace, it'll have a loop on it, and you'll be able to go in there and hook it quickly and bring it out of the furnace, and then do whatever heat treatment or quench or that you're gonna do to it. Okay. So what we're going to do at this point is set up the drill press correctly to operate it. The particular drill press we have here is my favorite drill press. In fact, I actually stole this from University of Wisconsin-Madison. And what's cool about it is that, unlike most drill presses, it's got actual dovetail ways for the tables to move up and down. You can see the actual spindle itself will move up and down as well. And the reason why this is good is because if I have, let's say, I'm drilling a hole and I'm going to ream that hole or I'm going to tap that hole, okay, you're going to use bits of much differing length, okay? And usually you only have maybe 4 or 5, maybe 6 inches of travel on your spindle, on the quill here, and therefore, if I drill a hole and then I want to ream it, and the reamer's 9 inches long, and my drill bit's only 3 or 4 inches long, I drill the hole, and now I have to move on these machines over here. I actually have to move the whole base down. But you see what happens when you move it? Because it's on a round column, you just lost the position of your hole. You can find it again, but it's hard to, and you might not locate directly over top of the hole again. With this particular drill press, we can loosen and move the whole spindle assembly up, and we can also lower the table pretty much down to the floor almost. Okay, so I could drill something with a foot-long drill bit or something like that, and then come back and drill it with a really small drill bit. So that keeps the spindle lined up with whatever it is clamped down on the table here. Okay, now typically you're going to want to, if you're going to be drilling larger holes, you want to clamp the whole vise down, and everything needs to be rigid before you go and drill a hole. Don't drill sheet metal on this. Okay, what happens when you drill a piece of sheet metal? You're going to make a propeller out of it typically. What happens is the drill breaks through the sheet metal and doesn't quite clear a hole, and it starts spinning around, and if you're holding on to it with your hand, it's probably going to take either a good portion of your skin off, or it's going to do some damage of some sort. Okay, there's special drills for drilling in sheet metal. They're called step drills. They have a zero rake angle on it and a straight up and down. The cutting edge is straight up and down. So when it goes through, it doesn't want to dig itself into it. If you look at a normal drill bit, it's actually spiraled. So when it cuts through, it tends to want to pull itself down a little deeper. One way of getting around that would be to take and put something fairly hard underneath what you're drilling, maybe a real hard wood or a piece of aluminum or something like that. So, and then clamp it down. So when it goes through, that it's going into something that's almost as hard as the material you're drilling. That's one way around it. The other way you can do that is you can actually grind the edges, the cutting edges of the tool straight up and down, so that the drill doesn't want to pull in. If you're drilling plastic, that's what you do. Like if you're interested, I'll show you how to do that on the grinder. It kind of ruins the drill bit, but I have a little box that says plastic drills on it, and they're drills that I've doctored to have a zero rake angle. Okay, it's just the cutting edge is straight up and down instead of being on an angle, so that it wants to suck itself in like a screw. Okay, we're drilling. This is a high-speed steel drill bit. It's made out of high-speed steel. It's not carbide or anything fancy. And so if we spin this too fast in a piece of steel, what's going to happen? It's going to start to get overheated. You could actually heat treat this piece of steel while you're drilling it, which, if it's hardenable steel, that's bad. So now you just created a surface that's as hard as the drill bit, and it creates more friction. Eventually gets red hot, and you either weld two pieces together, or you got a broken drill, or the drill's broken into your piece here. So we don't want to do that. We want to make sure that we're at the right speed in order to drill a hole in this. Okay, so how do we calculate that? A calculation for the cutting speed, or for the speed at which you turn this drill, the RPM that we set for this. This is one of the things I'd like you to remember as you go through. If you do the metals minor, you will graduate from here with this stuck in your head. And the equation is the RPM that you turn this drill at is equal to the cutting speed times 4 over the diameter. Okay. Now, and I'll give you the cutting speed is how fast the peripheral surface of that is turning. And it's usually in the English units, it'd be in feet per minute. So how many feet per minute is that surface traveling over the drill surface traveling over this surface? Where is it traveling the fastest? In the center or at the outside edge?
Outside edge.
Outside edge, right? It's like a merry-go-round. Okay, the center, you can stand in the center of a merry-go-round, you just turn it around. But if you're at the outside edge, you're hanging on for dear life. Okay? So the actual velocity at the outside edge is going to be the greatest. Okay? And that's where you're going to tend to burn the drill up, as on that outside edge. So we need to keep that periphery at the speed at which it's intended. You want to go fast in order to drill the hole in a relative, high speed, but in a minimum time. But we want to not burn the drill bit up. Okay, so cutting speed for steel, and we don't know what kind of steel this is. Okay, so we'll downgrade it a little bit. But typically for low carbon steel, with the high-speed steel drill bit, which is your standard one that you buy, not the cheapo ones, but a fairly decent drill bit, and that would be 100 surface feet per minute. That's a really easy one to remember. So 100 feet per minute would be for steel. So cutting speed times 4, the 100 feet per minute times 4, okay, over the diameter. Now, so that's 400 over. And it's about 1/8 of an inch, roughly, is the diameter of that. Okay, so when you divide it by a small number, it gets bigger, right? Comes out, I think it was it was like 3,100 RPM or 3,200 RPM. So you want to punch it out on their little calculator that they can. We only have certain choices here, though. The highest choice is 3,200 RPM. And remember, I want to downgrade it a little bit because of the fact that this might be a tool steel, which needs to be cut at slightly slower speeds than with a low carbon steel. Okay, and so my choices are 3,200, and the next one down is 2,200. Okay, I prefer that you don't do this. I'm going to show you this, but this has 2 cone pulleys, and you can see that we're on the second speed down, the fastest. Here's the motor. That's the big end, and this is actually going a little bit faster than this, because you can see this diameter is slightly larger than that diameter. And so that would be one of the higher speeds. If you're going to buy a drill press for yourself, the only thing I don't like about this machine is that I would want to put another set of cone pulleys right in the middle here, an idler one. And the idea is that you can have more range in your speed, both in the high end and the low end. Okay? So if you're buying one for your basement or something like that, make sure it's got the double set of cone pulleys. The other thing I would do is make sure it has the longest travel possible with the quill, okay? Because it's probably going to have a round, frame, and so every time you move your height, it's going to change your location. It's hard to find drill presses like this. If you do find one, a lot of times the old ones of these will have the big wide leather belts on them and a big motor down here. Okay, and you can take those and retrofit them. They're bigger than this though. And they're really nice though. So if you got the room, I'd buy one. Okay, let's drill a hole. We've got the right RPM set. This is a special vise here. This vise can be actuated by this lever. You can see it's got like basically a cam lock system. Okay, and the cool thing is I can move it back like this. So it's really fast. Okay, they don't hold quite as well as maybe a machinist vise or something like that. But for doing stuff in the drill press, it's really nice. So it's got a little burr on the one edge here, and so I'll put that burr on the downside. I'll put it between the jaws, so it's going to sit flat. And also, you notice that I'm putting the sample in the middle of the jaws. You put it on the edge over here, and what happens? It tends to torque on the. It's not good for the vise. Okay, to clamp on one edge of it. So always clamp in the middle, if at all possible. If you don't want to clamp in the middle, if you have to have it over here for some reason, what would you do?
Something on the other end.
Put something the same diameter on the other side. Okay, so that way we have a it doesn't clamp down over there. Okay, so right there, clamp it down. You also notice that there's a lot of holes in these jaws, these aluminum jaws. If you don't do that, please. Don't drill into the jaws. So we're going to drill between the jaws and avoid drilling into the jaws. Okay. We're going to use a little bit of lubricant. Okay, this is an oil-based cutting fluid of some sort, and we're going to squirt a little drop of that on there. You might do it a couple times while you're drilling. We're also going to have to get this thing down in the vicinity that we want to drill. Moved it up. Okay. One thing that I didn't get to show you is that this particular chuck arrangement is it's just held in there by a taper. Okay, and you can see there's a little dog on the back of it. That dog keeps it from spinning around, but the taper itself actually is pretty good at keeping it from spinning as well. This is called a Morris taper. This is a number 2 Morris taper. All the rest of the equipment here has number 3. Okay, so I think there's only one of these chucks. If you would want to use this on number 3 Morris taper, you'd put this adapter right here, and that's number 3. Okay, in order to use that, it's a self-holding taper. In other words, it will hold itself on there if you do a couple things. First of all, you got to tap it on, but you got to make sure it's clean. There's no oil on it. Actually, oil's bad because the oil will keep the taper from seating on the other one. It's actually that film, that hydraulic pressure in there, will keep it from seating, and it'll fall off while you're drilling with it. Okay, so you want to make sure they're dry and clean, like no chips in there. Any little chips from machining inside the spindle or on your taper will also cause it to release prematurely or in an unsafe condition. Okay, so this is called a drift, and that's how you remove it. There's a rounded side and a flat side. You put the flat side down. That's what pushes the dog on the dog and pushes it out. Okay. Okay, so you put this in here. You want to tap it in so it doesn't fall out while you're drilling with it the first time. Usually after you drill your first hole, it's seated pretty well and it's not going to fall out. Okay, but you don't. The first time you start drilling, you don't want it to fall out. Okay. Now, oops, that's not in there very well. Chuck key. Okay, so this is a substandard length drill bit. This is for a screw machine. And it looks like we're drilling pretty close to the, you can tell by the color on the tip that we're really close to the maximum temperature that we can drill. Or do that, or someone didn't lubricate it or something. We've already drilled probably 18 or 20 holes with this. Okay. One thing you're going to need to know about drill bits is the shank on the drill bit. Okay, this area up here, that is actually softer than the rest of it. So some people think that if they put the drill bit all the way up in the chuck, they get better support on the drill. Actually, that's the opposite of it, and you're going to screw your chuck up. Okay. You want to grab up here, you know, let's say about a quarter inch or so away from where the flutes start, because that is actually has a different heat treatment, and that's soft, and the jaws will grab into it. Everything from there down has been hardened, and the jaws will not grab on it and will slip and spin. Okay. Or be more likely to. If you put a lot of torque on a drill bit, it's likely to spin around. And it looks like someone's got not exactly the best chuck key on here. That's not good. Okay, so what happens if you take, especially a longer drill bit, and you start drilling with it? Just come down here and start drilling. What will happen? It tends to walk across the surface, and your drill bit doesn't go in the hole where you want it to go. Okay, so there's a couple ways around that. We can take a prick punch and make a little mark there, and so when the drill comes down, it's got something to bite into, so that the chisel edge, where there's basically no point or no sharp edge, will start to push into the material. A little trick of the trade is if you get it right where you want it, and you're careful, you can kind of do this kind of tapping, quick tapping action, and that will start your drill hole. So I'm going to put a little drop of, oop, that wasn't a little drop, that was a big drop. Make sure when you're done, there's some paper towels over here, clean up the machine, get all the chips off of it, and the oil. Okay, so I'm going to turn it on. Come down. Okay, now I've created a little spot that I'm going to drill. You can stop every once in a while and look at how the hole's going. Maybe put a little bit of oil down in the hole. Nothing to it. Okay. So that drill bit's sharp. If we were having to put a lot of force on that, I would tend to think that drill bit's dull, and I would sharpen it. Okay. There's a couple ways to sharpen it. You can use a machine to sharpen drill bits, or you can do it by hand. Anything smaller than about 1/8 of an inch or smaller tends to get really hard to do by hand. If you can use a loop or something like that, and a little bitty Dremel tool, and you can sometimes sharpen these little bitty ones. But above 1/8 of an inch, though, you can use a regular grinder, and you can put an edge on a drill bit if you know what you're doing. You can also screw it up really quickly. Okay, both edges have to be the same length. They have to be the right angle, and they have to be the right angle in two directions, actually. So I can show you how to do that. If you're going to be a tech ed, you want to learn how to do that. I'll actually show you personally how to do this. Now we have a hole through it now, and that hole will have a burr on the top and the bottom, as well as where we cut it off before. Okay. The problem is that when we take the first initial hardness, if there's a burr on there, the hardness puts 300 kilograms on the sample, okay, on a little bitty indenter. And we're measuring a small movement in the depth, a small movement in that indenter. If there's a little edge that can get crushed, it will likely get crushed, and your hardness will be thrown off really badly that way. So the thing you're going to do after you drill this hole, or even before you drill the hole, is take it over to the sandpaper and to remove those burrs. So let's do that next. Okay, at this point what we're going to do is we're going to take and we're going to remove the burr. We've got some sandpaper down on the table here, and we'll just put a little bit of water down just so that it lubricates, it doesn't plug up the paper. And by the time you're done with this, you're going to have probably callus, the tips of your fingers will be somewhat callous because you've got a sharp edge there. If you really feel inclined, we can, and you've looked at the grinder video, we can go over and grind a little chamfer on that edge. That makes it a little bit nicer to hold on to, so it doesn't have a sharp edge. So this one here, I've got it pretty much, the burrs all removed because I can see scratches all the way across the surface now. Okay, that would be fine to go and do the hardness to the other side as well. By the way, it's a lot harder after you've done your first heat treatment, especially, because if it becomes hard, it's harder to sand. Okay, so you might as well do this on both sides the first time around. And we're not quite there. I see a little bit more material that has to be removed. Every time you heat treat this, it'll have a bunch of scale on the surface. Okay? So when it has scale on the surface, you have to get all of it off until you get back down to the shiny metal again. Okay, so that's good on that side. Once in a while, what happens is if you get a really nice oxidized surface and you sand it, it'll look like it's kind of shiny. But if it's not like shiny silver, it's shiny gray, you just basically polish the iron oxide. Okay, you need to break through the iron oxide and into, especially when we do the annealing where it's been in the furnace for 10 hours or something like that. You need to break through that, and you want to actually sand into that base material a little bit. What happens is, on the surface, carbon actually goes off and forms carbon dioxide. So you lose some carbon, and we're trying to determine the carbon content of this. So the hardness may vary slightly just on the very surface of it. So if you get down a little bit, you're going to be better off. So a little bit extra time on the sanding is not going to hurt you at all. Okay, I don't care if this ends up, a few thousandths thicker or thinner at the end of it. That'll be not a big deal. Okay, so dry it off, and then we'll take it over to the hardness tester then. Okay, here we are in front of the hardness testers. We have two hardness testers. It's a Wilson Series 2000 electronic hardness tester, and then a Wilson manual hardness tester from a few years back. Both of these do exactly the same thing, and you'll get the same numbers from either of them. Okay. The way we decided to do this is that your first test is going to be on the automatic one, okay, and the second test, if you need to perform it, will be on the manual one. And you will have to use both of these machines. So what we decided to do is to have the Rockwell C scale, which is the harder scale that we're going to be using for testing on the automatic one. And the indenter is a diamond. So right here is a little diamond attached to a piece of steel. Okay. It's not very shiny or anything. It doesn't look like something you want to put on a ring. But on the tip of that, there's a diamond. You got to make sure that that doesn't have a crack in it. If you drop this or you smack it against something hard, you could actually crack that diamond. So these are expensive. Don't do that. Okay. So there's the and they call it the Braille diamond indenter. Not sure why, but it's called a Braille indenter. Okay. And then this particular test will put 150 kilograms. It'll first put 10 kilograms. It says right here, 10 kilograms preload on it. It'll come down and put a 10 kilogram preload, and then it'll put 150 kilograms, like 300 pounds, on that little diamond. So there's it will push it into the surface of this piece of steel. If it's hard, it won't go in very far. If it's soft, it'll sink in deeper. And it has a very accurate scale inside, a micrometer scale that it measures. Now in this case it's electronic. That it measures how deep that indenter actually sunk between when it was 10 and 150 kilograms. Okay? And that's how it measures the hardness, is that depth of penetration. This one here does exactly the same thing. This one is set up for the B scale, but it could be set up for any scale. And the indenter is not a diamond anymore. This is for softer materials. Okay, so this one has, kind of hard to see, but this is a 1/16 of an inch diameter ball mounted on a little bitty pedestal, basically a little bitty ball bearing. Okay, and so it's hardened steel. Okay, and if that gets dented, we can put a new one on there. But the idea is that we won't want to dent that, right? How would you dent this? Put a flat on it. Basically, you would pick a hardness of something like, hardened high carbon steel or something like that. Okay, if it had a Rockwell hardness of 55 or 60 or something like that, which is a high number, it would be almost the same hardness as this little ball on here. So we're going to probably put a flat on it. So that's why you always test with this one first, and if it's a low hardness, then you come over to this one over here. What's low? Well, below 20, Rockwell C, which is this scale, it's not accurate. So anything below 20, it'll give you a hardness number, but if it's below 20, it will give you not a very good one. Okay. So, because what happens is basically the diamond has completely embedded itself into the steel, or whatever material it is you're testing, and you've gone past where the diamond is, okay? And so, on the 16th inch ball indenter, we use 100 kilograms load, and it's a bigger surface area. So now it's for softer materials. Once I put the indenter back in there, we probably want to do one test before you start taking data, because that indenter needs to get seated. Remember that we're measuring like, very like tens of thousands of an inch, and that will have a difference on what the hardness reads. Okay, so if I just put that in there and there's a piece of hair or something in there at 10 kilograms, it might not crush the hair, but at 150 it will. Okay, and the next time around it's already crushed and we're good. Okay, right? So seating the indenter is important. Okay, so first we're going to start out on the automatic tester. It should say ready for test. If there's something wrong with it and it's not cooperating, it's a little bit flaky. The humidity over the summer here is not good for this particular unit. You can see that the screen's already doing some weird stuff there. So we'll take our sample. We'll take our hardness not near the number 3, not near the drilled hole, but also not too close to the edge. If you put it right next to the edge, there's a couple things that can happen. First of all, it can actually flip the sample out, because we're putting 300 kilograms right on the edge of this. It might actually scoot it across the room, okay? And it puts a side load on the indenter. That's bad. So we want to put it in from the edge like about a 1/16 of an inch at least, okay? Also, if we're right next to the edge, you think about it, you put a stress here, it's deforming the metal in all directions. If it's easier to do it in this direction here, you're going to have a wrong hardness. Okay? If I was to take a hardness on this curved surface here, would I get the same number as on the flat? No, because it's easier to spread it in this direction because it's curved away from itself, right? So you can correct. If you push this button here, it says correct, you put a diameter in there, and it'll correct. There's a fudge factor that they use for a certain diameter to bring the hardness back to what it would be on a flat surface. Okay, we can do round things by using special anvils. Okay, this anvil is a V shape. You can put a round bar in there or something like that and take a hardness of it. Okay, there's a couple different ways, different anvils that you can put in here. This one's a small V. One thing you have to do though is if you got a part that's really long and it's kind of cantilevered out here, you'd have to put that on a stand or make sure it doesn't move while you're doing the hardness. Because remember that small movements, you can't hold on to it accurate enough. Small movements and a big lever out here is going to throw the reading completely off. Okay. Okay, so let's close in on that, and we'll. There's a light on here too. It's kind of neat. And we're going to take a hardness. There's an up and down arrow here, and that just basically moves your indenter up and down. Please don't run it right into the surface. It doesn't know that there's a surface there, and it gets going pretty quick. So you just kind of keep pushing the button until you're probably within 1/4 of an inch. You got to be patient. It takes a couple seconds for it to do what you tell it to. Okay. That point, if it says ready for test, we're just going to hit start. You got to kind of push the button down hard and hold it for a second, and you'll see it says waiting to contact the surface, putting the preliminary force on it. Okay, major force, and returning 7.5. What do we got to do now? We got to go over to the B scale because we're below 20, and if you see this indentation in here, it's pretty deep. Okay, so we're past that diamond. Okay, so we're going to move over to the B scale, and this one is a lot more complicated to work because it's completely manual. So what happens with this one is that back here there's some weights, and right now we have the largest weight off of it. This is for the 150 kilograms. It says 60 plus 40 plus 50 is 150. So each one of these little weights on the back stacks up, okay, and makes what we're trying to do. Now, for a B scale, I have to use a 1/16 of an inch diameter ball with 100 kilograms load, and I'm going to read the red scale on here. And that's where most people get screwed up with this, is they read either the wrong scale or they read it the wrong way. So that's what this video is all about, is to remind you how to do it in a way that doesn't give you wrong data. Last semester, one whole class had the wrong data for some of their samples. Okay, so we had to throw pretty much all that data away. And you guys are going to have to sort through all that data and try to figure out what went wrong. Okay, I'm sure it won't be you guys, but okay. First thing we want to look at is that this lever here, this little silver lever here, is in the kind of the back position. It can flip forward and it can flip back, and it's in the back position right now. Okay. The reason for that is when we flip it forward, it takes this load on the back and puts hydraulic weight onto that indenter. Now, that's not 100 kilograms that I have on there, but when it goes through the hydraulic cylinder and the magnification of the load through that, it will put 100 kilograms load onto that indenter. Okay, so this says 50 kilograms on here. It's 100 pounds. I don't think so. Okay, unless it's made out of uranium or something like that, which would be bad. So I'm going to move out of the range of the little 3 on there. Okay, so now what do? We're going to put that preload on there. Now this doesn't do it automatically. You have to preload it. And the way you do that is you bring the actual anvil up. Okay, there's a little sign on here that says loosen in this direction. This would be tightened in that direction. So this little ship's wheel here turns in that direction. And we're going to watch it, and once it contacts the surface, okay, what you'll see is the scale will start to move. We want to close in on that, maybe even come right up here. Okay, kind of get where you can see, guys. So I'm going to start bringing that up a little bit more, and what you'll see is the big arrow is moving, as well as this little one's moving slowly. Okay, and what we're going to try to do is get the large needle to be vertical when the small needle is also vertical. So we got one more revolution to do. This is doing that preload on the sample. Oh, pretty good. Okay, it's not easy to do that. So let's say I went a little bit past it. Oop, crap. What you can do is, it's got a little, hey, you screwed up, so I can move the set point a little bit over that way. Your 10, it's not very sensitive on the 10 kilograms preload. And so I'm going to make the set point right there. Now the weird thing is that if you read the B scale, which is the red one that you're supposed to read, it says B30 right there. But it says, in red, it says to set it there. You do want to set it there even though it's not at 0. It's weird. But okay. So now we've got it set. This little lever here is this little kind of collar is what we use to move that scale back and forth so that our set scale is right on 0. Okay. Try to get straight up and down, but it doesn't always happen. Okay. At this point, I'm going to put the full load onto the indenter. Okay. And the way I do that, there's 2 actual ways. One is I can push this lever in the front, which releases this handle, or I can just flip the handle forward. This lever is kind of it's kind of the high-tech version of a long time ago. Okay. There's a light there too. Okay, so if I push this lever down, and what you can see that the actual handle is still turning. It takes a while for the hydraulic force. It doesn't do it instantaneously. It takes a while for all the hydraulic force to be put onto the indenter. 10 to 20 seconds. You want to wait until that completely moves forward. Now, if I were to read this right now, I would be completely wrong. And that's what they did last semester, I believe. Because we have the force on it, and our indenter's moved down, but we haven't moved it back up to measure that distance yet. Okay. A little hint here to give you an idea whether you're in the ballpark. Okay. There's a conversion factor right on the front of here. The equation's right here. This is an approximation, but it's pretty good for what we're doing. Rockwell C is equal to Rockwell B minus 80. Okay. So let's say I got a number like 100. on the Rockwell B scale, what would be the Rockwell C reading?
20.
20. Okay, are we below 20 over here? Okay, so what? So what would it actually, our number actually be, you think, on B scale, if you're running this equation backwards? Okay?
87.
Yeah, 87.5. Okay, so what does it read right now? 65. That would be an indication that something's wrong. You need to flip this lever back to the vertical position in order to read it. Okay, so do that conversion and make sure that the number makes sense. Give yourself a reality check. Okay, we're at 95. Okay, so that's not accurate. Okay, this is going to be a more accurate number, and it's within, let's say, 10 Rockwell hardness points. You're probably going to be fairly accurate. Okay, so I would have suspected that would have been more down by 90, but remember that this is the first hardness I took, and it hasn't been seated yet. So let's do another one real quick. Now, if I go and start torquing on this to make it tighter, that's going to be bad. Okay, so if I turn this little lever here the wrong way, so that right there it says loosen is this way, so I'll do that. It takes the preload off of it, and I'm going to move over a little bit, and let's do another hardness. Okay. Okay, this time I'm going to get it right on. By the way, if you go past it, don't go backwards again because you've already deformed it somewhat. So just stay where you are and move the scale. If you're way past it, just move to a different location. Okay, just take the load off of it and move it to a different spot. Sometimes it kind of sticks a little bit and you end up going way past it. Okay, so I'm going to move the scale back to where it's supposed to be for set point. Okay, and then I'm going to release the lever. Okay, we'll wait till it completely gets to full force. And it looks good. Flip it back. Okay, still around the same spot. So we would take 3 readings that are fairly repeatable, let's say within 5 Rockwell hardness numbers. Okay, so you want to do at least 3 tests. If one of them's crazy, some different number, okay, take 4 or 5 and then take the average of the ones that are repeating. Okay, so loosen it up again. You're going to do 3 hardnesses minimum that are similar to each other for every heat treatment that you do. So you do initial, you get your initial stuff, then everyone goes together over to the furnace and puts them in at the same time. They're in there for a half an hour. Then everyone pulls them out at nearly the same time. So everyone suits up. You go over there and you get your wire on here. Okay, it's in the furnace. They've been in there for half an hour. You grab it and you bring it out and you quickly do whatever it is you're supposed to do. If I'm quenching it in air, it doesn't matter, how fast you put it. It's in air, right? Okay, you put it on the bench and you let it sit there until it cools down. There's a special bench with a ceramic top on it. Okay. But when you're doing water or oil, what you're going to have to do is you pull it out and you put it down in the liquid, and you have to move it around really quick. Why? Because what happens is once you put it down in the liquid, it forms a vapor bubble around, especially with water. Because you have steam now, it forms steam, and the steam is fairly insulating actually compared to it. If you take water and put it all over your hand, I've stuck my hand in molten lead don't try this at home. Put my hand all the way down in a crucible of molten lead. Okay, of course they bet me a lot of money to do that, and it was really kind of weird, but it actually did protect your hand. Get your hand wet, and the steam protects your hand for about a second and a half. Okay, after that it's going to be bad. But same thing happens here. You put the sample in there, and I'm trying to cool it quickly, and if I'm not moving it around, I get that vapor barrier around it, and it basically doesn't cool as fast as it should. Okay, so get it in there, move it around. Meanwhile, if the furnace is sitting open, all the other 5 samples are cooling down. We don't want that. Okay? So what do? There's a furnace, someone's on the furnace, they open the door, it's only open for a second, close it back down right away. Okay? You know, not dangerously so. Don't drop it down, but open, closed, kind of like, you know, you only have about a second to get your sample out of there. So you got to place them in the furnace when you put them in there so that you can get at them quickly. And you got to know which one's yours. So that little wire that you bend up, you want to bend that wire in a way that it's identifiable to you from the furnace when it's at 1500 degrees or whatever. That's actually 1600 degrees. So it's at 1600 degrees in the furnace, red hot. You got to grab it and quickly put it into whatever it is that you're trying to cool it in. Okay, and then move it around. Okay, let's go over and look at the furnace, and we'll see how, you know, what you have to wear and how the furnace operates. Okay, at this point, what we're going to do, here's the furnace we're going to be using. It'll vary from year to year, but this is a Spirotherm furnace. It's gas operated, and it has very high BTU output. We also have an electric furnace, which right now is being repaired, and that one does not have as high of a thermal output. So what we have to do is, if I open the door on this one, it'll be up to temperature in maybe 30 seconds to a minute. Okay, with the electric furnace, it might be minutes. Okay, so that one's a lot more critical on the door operation than that. On this one here, and the door is kind of hard to operate. You put your foot on this pedal, and you can see this pedal kind of spins around. Okay, and when you get it to all the way in the back, it hits a notch that allows it to go down. I also put my hand up top here. Don't get it underneath this chain, but I can kind of help lift it. Put my hand up there. Okay. Good. So what I'm going to do here is I'm going to create with some welding wire here. I'm going to create a unique shaped loop that when I'm looking at it in the furnace, I can tell that it's mine. Okay? So you need a piece about, I don't know, that was about 10 inches or something long. And you can take it, you first put a little twist up near the actual sample itself. Okay? And then make it so it wants to stand straight up. So you want to twist that fairly tight around here. If you make it too tight, sometimes you'll break the wire, but you'll figure that out. Okay, now it kind of wants to stand up. So now I'm going to bend this in some sort of a loop arrangement so I can identify it as mine. And twist it back together. You can do something with the little antenna on the end, however you want to do it, just so that you know it's yours. I'm going to twist it a little bit more down the bottom here. I'll probably break it, but okay. Now, if I were to put this into a warm furnace, I would want something like this little hook here, in order to put it in there. Okay, and make sure your little antenna things don't get in the way of. You can cut those off. I've got some snippers there as well. Okay, so you're going to put this in there, and you might arrange them about halfway in the furnace crosswise, or you could put them all in front of each other so you can do it sequentially. It doesn't matter, just so that you can get in there and grab it. And you don't want it right by the door because the temperature by the door is lower than farther back. Inside of the furnace, there's a thermocouple. A thermocouple is the temperature measuring device. It's way in the back, in the middle. Okay. And that is where it controls its temperature to. So if the temperature in the front is a lot lower than that, it doesn't know that. So you want to be kind of closer to that a little bit, but not so far that you have to, stick your head in the furnace there to figure out where it is. Okay, it's going to be 1600 degrees, which is really hot. In a couple seconds here, I'm going to show you the safety gear that you need to wear. Can you point out anything that I shouldn't be wearing today that I am? I have polar fleece on. That would be a bad thing to use to actually operate this furnace. Okay. So when you guys, cotton, it's okay. But you're going to put a flame retardant jacket on. Okay. goggles, face shields. It'll be so hot that your facial hair might tend to start on fire or something if you stick your face right down near it. Okay, the radiant heat is very intense, 1600 degrees. You want to have cotton pants or natural fiber pants, and then shoes should be leather. Okay. Anything else? Gloves, leather gloves, like welding gloves. Okay. So we'll suit up, and then we can operate the furnace. But essentially, you're going to take your sample. It'll be sitting there, and the furnace will be on. It'll be very loud, so you won't be able to talk very well. And then you stick your deal in there. The door closes right away, and here's a bucket of oil. You'd go in there and move it around, or a bucket of water, whatever it is that you're going to use. And you quickly wiggle around and get it down to temperature while this thing gets closed again. So you'll all have to kind of suit up and kind of get in line, and then pass the face shield. There's like only four face shields, so pass the face shields along as you go. Okay, and then one person will be operating the furnace maybe the whole time. Okay, so you'll have an expert furnace operator until it's their turn to go and quench their sample. Okay, I'm going to start up this furnace after I put on my safety gear, so I don't want to start on fire, and then we'll show you how the furnace operates. Here, there's different sizes. Pick the size that fits you. I'm going to need a face shield from over in the grinding area there. So you can do that, please. Okay. Okay, so getting all buttoned up. Thank you. By the way, don't try to clean these off with like your sleeve or something like that. That's what just scratches them. If you want to clean a face shield off or your safety glasses, you clean them off with water in the sink and some soap. There's some dish soap in the front room there, and that way you're not rubbing sand particles or whatever's in the air here onto the surface of the plastic, which makes it scratch. Okay, so leather gloves. Right here. Make sure you get some overlap at the sleeves. No holes in gloves are bad. If you have a hole in the glove, make sure you show it to me, and together we'll throw it in the garbage. Okay, so we're going to turn on this furnace, and I'm going to take this off of here to let you see better what's going on here. That's interesting. This particular little deal here is for when we do lost wax casting. Okay, here is the controller for this furnace. Right now, the orange little set point is at 1600. I can move it back and forth with this little dial here, and you want to make sure that's at 1600. If someone comes in here and is using it for something else, the class before, and I forget to check it, and you don't check it, your data is still screwed up. Okay, so it's on you. Okay, there's also a green, like a fluorescent green little needle. And that's the actual temperature. It's reading right now down at 0-ish, or close to 0. And so I'm going to turn on the furnace, the black button here. Air comes on. Pilot light comes on. And then it ignites. Usually. There's 6 burners in there, and they're radially, it's like a spiral. So you can see it, there's a lot of heat going into that thing. Okay, it takes about 15 minutes to get up to temperature. You want to have it up to temperature for about 5 minutes before you stick your samples in there. So if you're doing heat treatment that day and you don't hear this loud noise, get in here and turn this thing on right away, or tell me about it, so that you don't stand around waiting for something to do. Okay? We also got to make sure this vent is on, and the switch is right over here. Otherwise, we're putting a lot of, And essentially, you're going to pull those out with that, after that temperature, you're going to pull them out, you're going to quench them at different, you're going to quench them at different media materials, and you're going to take and you're going to do the hardness test. You're going to sand them off, do the hardness test, and record that data. Okay, one thing I want you to remember is that all the data, when you put it in the spreadsheet, is going to be put in Rockwell C units. So you got to convert the data. You might take 3 points in Rockwell B. You convert the data to Rockwell C, and you put all 3 of those points on the spreadsheet. Okay, so you can see what what the variation is. Ideally you put raw data in there, but people get confused then. Was that a B or is that a C value? So if everything's put in as C, then you'll have to do some conversions probably, but that's up to you to make sure you do that right. Any questions? Okay.